Okay guys, here is the key for the first quiz we had this year. This covers 1-1 to 1-5. So the first problem, you're going to write in interval notation. That would be all numbers less than negative or less than or equal to 4. So that's going to be from negative infinity, and you never include infinity, so there's a parenthesis all the way to positive 4. We include 4, so we have a bracket. If you graph that set of numbers, you can graph it up here. That would be a colored in circle, and that would be at 4, and all numbers less than would be to the left. So colored in circle again is for equal to. It's including 4. Number 3, write this as an inequality. So from negative 2 to 4 as an inequality, that's going to be all numbers in between negative 2 and 4. Okay, now are we including negative 2? That would be no, because of the parenthesis. And are we including 4? Yes, because the bracket, so we have to have the less than or equal to. Graph that set of numbers. That's a redundant question. Well, it actually is graph below here. So the graph would be, that was kind of a stupid question on my part. Something to fix for next year. So there's the graph. And of course, writing as an inequality, that also is redundant. And interval notation, that was just poorly written on my part, so we will skip down to question number 7. Explain how you can estimate the square root of 51 without a calculator. Well, hopefully you know your perfect squares and that 51 lies in between the square root of 49 and the square root of 64. Which the square root of 49 is 7, the square root of 64 is 8, and I'll say that 51 is going to be somewhere closer to 7, so I said, anywhere around approximately 7.1 will work out. Down to the radicals, we have 3 square root 32, so we want to squeeze any perfect square radicals out of this as we can. So we think about factors of 32, and 16 comes to mind. So I'm going to factor this as 3 times the square root of 16 times the square root of 2, which is then 3 times 4, or 12, square root 2. Now, how do you know you're done? Well, when you can't factor any perfect squares out of your radical. And 2 is a prime number, so there's no way we can factor anything out of there, so we're done. Move over to number 9. Now there's a little bit of a trick to this question, or a efficiency. A lot of you probably tried to multiply these together without a calculator, and you were groaning about that, but you really didn't need a calculator if you realized that 42 and 18 have common factors of 6. So if I broke 42 down into root 7 times root 6 and 18, somebody's walking on the roof right now, and it's making the projector bounce. I don't know if you can see that or not. Anyway, back to the problem. Root 7 times root 6, maybe it was Santa Claus. He might be practicing. Back to the problem. Root 7 times root 6 is the same as 42, and root 6 times root 3 is the same as 18. So now what I have here is I have a pair of square root 6's. And we know that root 6 times root 6 is just 6. It's a perfect square, square root 36, which ends up being 6. So this is then 6 times the square root of 21. And 21 cannot be reduced any further. There's no perfect squares there, so we're good to go with that. Same type of thing, jump down to 10 here. 10, we have the square root of 14 as a denominator, and we want to rationalize that and get the radical out of the denominator. But so maybe you decided, okay, well, let's just multiply by square root 14 over square root 14, and then rationalize, and then you're going to get a giant numerator that would be the square root of 63 times 14, whatever that is. And what I'm saying is you don't necessarily need to do that. So let's go ahead and work a little more efficient. And let's see if we can find a common factor here. So 63 has a common factor of 7 with the denominator. So we're going to factor 63 as 9 and 7, and 14 as 2 and 7. And then we can go ahead and take the 7s, because root 7 over root 7 is 1, and we can just simplify those out of the expression. So now we have root 9 over root 2, which after we rationalize that is going to be, square root 9 is of course just 3. So we are going to have 3 over the square root of 2, which is, after you rationalize that, 3 root 2 over 2. All right, moving on to number 11. We have a square root 2 in our denominator, and we are not supposed to have the square roots in our denominator. So the tendency here is for students to just take these root 2's here and just cancel those out. But that's illegal. That's an illegal move. You cannot just do that, and here's why. If I had, let's say I had, this is impractical, but let's say I had 2 plus 4 over 2. Okay. Now you should know that that's supposed to be 6 over 2, which is 3. 6 divided by 2 is 3. Okay, so, but if you just canceled that out, like the root 2's out, that would be the same as just taking these 2's and going canceling those out and saying, oh, this is equal to 4. Well, it's not equal to 4. It's equal to 3. So what you did there was something that violates the laws of algebra. That doesn't work that way. So you can't do that. So what we need to do to avoid making that mistake is separate these. So before you rationalize or after you rationalize, doesn't matter, you are going to separate these as 2 root 3 over root 2 plus 4 root 2 over root 2. Okay, now you see here, we're not adding anything with the 4 root 2 over root 2. They're factors, so now I can go ahead and say root 2 over root 2 factor is just 1, so those are gone. So this is okay to do, but what we talked about before is not. And then over here, you want to rationalize this root 2 out of the equation, so I'm going to multiply this by root 2 over root 2, which is going to give me, and forgive me, I'm running out of room here, but it's going to give me 2 root 6 over 2, and then the other part, remember, was just 4. Okay, and then I have a factor of 2 over root 2 over 2 that I can get rid of. So in the end, that's how we got root 6 plus 4. Okay. All right. All right, here we go, number 12. We want to add or subtract two radicals. We want to have the like radical terms, which means that these two radical parts have to match. Now, if I factor out a 4 out of the 20 and a 9 out of the 45, they will match. So let's go ahead and do that, and let's factor square root 20 into 4 and 5, minus 7, and then 45 into 9 and 5. And then, of course, 4 is a perfect square and 9 is a perfect square. So what we'll end up here with is negative 4 root 5 minus square root of 3 is, or square root of 9 is 3, so that's 21 root 5. So now, since they have the like radical parts, I can go ahead and subtract them and make one term, which would be negative 25 root 5. Okay, number 13, I want to rationalize the denominator and get rid of that 8. Before I do that, I could go ahead and simplify, but it's not going to be too bad. It's not going to be a huge number, so I'll just go ahead and rationalize the denominator, get rid of that radical in the denominator here, and I'd have 4 square root 24 all over 8. And of course there's a factor of 4 in root 24. So square root 24 is the same as root 4 root 6. So together the root 4 and the 4 make 8, which then I move down here would be 8 root 6 all over 8. And the 8 got cut off there, but those then would cancel out. So this is then root 6.